This video series focuses exclusively on the mathematical analysis and modeling of chemical systems, examining them through problem solving. These modeled systems lead to the formulation of differential equations that admit analytical solutions, that is, solutions that can be expressed using one or more mathematical expressions. We begin by analyzing systems that give rise to first-order differential equations. The simplest example of such a problem is a mass balance in a stirred tank. The figure shows an ideal stirred tank that initially contains a salt solution occupying half of the tank's total volume. The initial concentration of the solution is given. At a certain moment, a feed stream with a known concentration enters the tank at a constant volumetric flow rate. Simultaneously, an outlet stream leaves the tank at a flow rate equal to half of the inlet flow rate. Since the inlet and outlet flow rates differ, the solution accumulates in the tank over time. As a result, both the volume of the solution and its concentration change with time. The question we want to answer is, what is the concentration of the solution at the moment the tank becomes full? To answer this question, we must develop a mathematical model that tracks changes in both concentration and volume over time. Because this model is based on material balances, we begin by defining a control volume around the tank. The surface that encloses this control volume and separates it from its surroundings is called the control surface. Any flow crossing this surface represents material entering or leaving the control volume. In general, a mass or mole balance for a control volume is expressed as input plus production minus output minus consumption equals accumulation. Input is the amount of mass entering the control volume during a given time interval, while output is the amount leaving during the same interval. Production and consumption account for mass created or destroyed by chemical or nuclear reactions. Accumulation represents the change in mass within the control volume over the time interval. Since no chemical reactions occur in this problem, there is neither production nor consumption, and the mass balance simplifies accordingly. We first perform an overall mass balance for the solution, meaning the mixture of solvent and salt over the time interval from T to T plus delta T. The mass of solution entering the control volume during this interval is equal to the density of the inlet stream multiplied by its volumetric flow rate and by delta T. Multiplying density by volumetric flow rate yields mass flow rate, and multiplying by time gives the total mass entering the system. Similarly, the mass leaving the control volume is given by the outlet density multiplied by the outlet flow rate and the same time interval. The difference between these input and output masses is equal to the accumulation, which is the difference between the mass of solution in the tank at time t plus delta t and at time t. Next, we perform a molar balance on the salt over the same time interval. The number of moles of salt entering the control volume is equal to the inlet concentration multiplied by the volumetric flow rate and by delta T. Likewise, the number of moles leaving is given by the outlet concentration multiplied by the outlet flow rate and by delta T. The accumulation is the change in the number of moles of salt within the tank during this time interval. These material balance equations allow us to calculate changes over discrete time intervals. To describe the system continuously, we let delta T approach zero. Dividing both sides of the balance equations by delta T and taking the limit leads, by definition, to differential equations. In this way, discrete balance relations are transformed into continuous continuity equations. This process yields a system of two differential equations with 5 unknowns. 2 unknowns correspond to the density and concentration in the tank, 2 correspond to the density and concentration in the outlet stream, and the 5th is the volume of solution in the tank. To solve the system, we therefore require 3 additional independent relationships. Because the tank is ideally mixed, its contents are uniform at all times. Consequently, the concentration and density of the solution inside the tank are identical to those of the outlet stream. This assumption simplifies the system to 2 differential equations with 3 unknowns. To obtain the final required relationship, we assume the solution is dilute, so its density is constant and independent of concentration. Under this assumption, density cancels out of the equations, and the system is reduced to its simplest form. These equations remain valid until the tank is completely filled. We are now left with 2 differential equations and 2 unknowns, along with known initial conditions. At the start of the process, both the volume of solution in the tank and its concentration are known. The first differential equation is straightforward to solve because the inlet and outlet flow rates are constant. Integration shows that the volume of solution in the tank increases linearly with time. Substituting this result into the second differential equation allows us to track changes in concentration over time. Before doing so, we expand the derivative of the product using the rules of differential calculus. With substitution and simple algebraic manipulation, we obtain a first-order differential equation describing the concentration as a function of time. This equation can be solved using separation of variables. By rearranging terms so that variables are separated, we can integrate both sides using the known initial concentration. The resulting expression involves logarithmic functions. Since all terms inside the logarithms are positive, absolute values are unnecessary. This solution gives the concentration as a function of time. Noting that the denominator in the expression corresponds to the solution volume, we can rewrite the result in a more compact form that directly relates concentration to volume. Applying logarithmic identities yields a relationship that allows us to calculate the concentration once the volume in the tank is known. As the volume increases, the concentration also increases. If the tank volume were infinite, the concentration would asymptotically approach the inlet concentration. However, the tank has a finite volume, and our goal is to determine the concentration at the moment it becomes full. According to the problem data, the tank is full when the volume reaches twice its initial value. Given the inlet concentration, the initial concentration, and the fact that the inlet flow rate is twice the outlet flow rate, we can substitute these values into our final expression to calculate the concentration at the moment the tank is filled. Although the given data initially appeared insufficient, this example demonstrates how a properly constructed mathematical model and mass balance can successfully solve the problem. Because we spent considerable time solving differential equations in this video, finding more efficient solution techniques will be important. I will leave this problem as an exercise for you to explore alternative approaches. I hope this video has helped you understand how to analyze and model a simple chemical system. In this series, mathematics is a necessary tool, but it is not sufficient on its own. Our focus is not merely on solving differential equations, but on interpreting the physical meaning of their solutions. Hoping these two questions have helped to assess your understanding of the analysis and modeling of this system. I look forward to meeting with you, albeit virtually, to solve a real problem in a future meeting.